One final example of an application to a first-order differential equation is using Newton's law of cooling. Newton's law of cooling relates that a function of temperature after time t, where capital T is the temperature, lowercase letter t is the time, is equal to some constant of proportionality of the temperature T minus the ambient temperature T sub m. Ambient temperature T sub m is just basically going to be the temperature that's around the object. So it's the environmental temperature. A lot of times it's called the ambient temperature. And so essentially what happens is you just take something that's hot, you put it into a cooler environment, and it's going to cool off. And we can figure out what the rate is at which this cools, and then we can also figure out how long it's going to take for it to cool. So we're going to take a look at an example of how to utilize this law of cooling to be able to get to some sort of viable solution to figure out how long it might take for something to cool. So we have a cake, it's removed from an oven, placed into a room with a temperature of 70 degrees Fahrenheit. Temperature is initially known to be 300 degrees Fahrenheit. And then after 3 minutes, the cake's temperature is 200 degrees Fahrenheit. So we have a function, and we want to create that function, t of t, that finds the temperature t minutes after removal from the oven. And we want to estimate how long it would take for the cake to be safely eaten. So right away we know that the ambient temperature T of t is going to be 70 degrees. So this is, I'm sorry, not T of t, but Tm. We know that 300 degrees is the initial temperature. So T of 0 is 300. And then after 3 minutes, when time is 3, the temperature is going to be 200. So now what we'd like to do is we'd like to be able to find some sort of equation to model that. Okay, so we're just going to stick everything into this differential right here. So we have dt, d capital T divided by d lowercase t is going to be equal to k t minus 70. A separable differential, very easy to solve. We're going to divide both sides by t minus 70. And that's going to be equal to k dt, and then we're going to integrate. So if we integrate, this becomes the natural log of absolute t minus 70, although we could just say t minus 70 because it's never going to get below that, is going to be equal to kt plus c. We're going to go ahead and raise both sides to the e power just like we've done numerous times. So that's going to be t minus 70 equals e to the kt plus c. We know the trick. E to the c is going to be some initial temperature. I'm going to call that t sub naught. We're going to add 70 to both sides. So we're going to get 70 plus t sub naught e to the kt. All right. Now we still have 3 unknowns. All right. So we're in good shape at this point, but we still have to do some algebra. We know that the initial value is going to be 300 degrees. So we can right away say that T sub naught is 300. Of course, if we don't believe it, actually it's not going to be T sub naught, excuse me. So we're going to substitute. We're going to say 300 is going to be equal to 70 plus t sub naught e to the k times 0. We know that e to the 0 is going to be 1. We can subtract 70 from both sides. So in this case, t sub naught is going to be 230. All right, so I do apologize, and as I initially thought it was 300. Good thing we substituted. So now we have a function t of t is going to be equal to 70 plus 230 e to the kt. We also knew that after 3 minutes, the temperature was 200 degrees. Okay, so 200 is going to be equal to 70 plus 230 e to the 3k. We could divide by 230, subtract 70, so we would get 130 divided by 230 is going to be equal to e to the 3k. We could take the natural log of both sides, divide by 3. So 1/3 ln of 130 over 230 is going to be equal to k. All right. And let's just go ahead and throw that in our calculators. So 1/3 ln of 130 over 230. I get negative 0.190 approximately for k. Let's just say 1902, so we can be pretty precise with this. So now we have a function, t of t. And our function t of t is going to be equal to 70 plus 230 e to the negative 0.1902 t. So that's our function. Now, the other question, so that was part A, find a function t of t that models, estimate how long it would take for the cake to be safely eaten. And of course that means that we have to know what's a safe temperature. So for part B, what's a safe temp? Right? So what we're going to do is we're going to go into Google and we're going to find ourselves a safe temperature to eat food. All right. Now it's probably going to be different. So I'm just typing in safe temperature to eat food. All right, not to heat it up or anything like that. All right. And when I typed it in, I start getting like stuff that says recommended minimum temperature, etc. So let's see. So I found a website. It says, what temperature is the range of food not to burn your mouth? And let's see, it says, I'm going to copy and paste this for everybody. This is actually pretty cool. So let me get out of here. So I found this on Stack Exchange, if anybody cares. But this was the distribution that I was given. And so it looks like that the temperature for a safe temperature, it was pleasantly hot at 160. 150 was pleasantly hot. Pleasant for soup 145. So maybe 150. All right, seems like a pretty good temperature. All right, so let's try that. So let's try substituting our safe temperature is equal to 150 degrees. All right, and let's see if we can figure out how long it would take for the cake to cool down to 150. It only took 3 minutes to get down to 200, so it shouldn't take an enormous amount of time. All right, so we're just going to set t of t equal to 150. So we're going to say 150 equals 70 plus 230 e to the negative 0.1902 t. All right, and that was the function that we just found, and I'm just setting it equal to 130. I'm going to subtract 70 and divide by 230, so we're going to get 80 over 230 is equal to e to the negative 0.1902 t. Take the natural log, divide by negative 0.1902. So ln of 80 over negative 230 divided by negative 0.1902 is equal to t. And remember, we shouldn't get anything that's astronomically long. If I were to estimate, since it took 3 minutes to cool down to 200 degrees, we're probably looking at somewhere, between like 5 and 7 minutes, 5 and 8 minutes or something like that. So let's just see what it is. I really don't know. So ln of 80 over 230 divided by negative 0.1902, and I got 5.55 minutes. All right, and that's pretty reasonable, right? Again, we always want to make sure that our solutions make sense. Okay. All right, so hopefully this is a usable application for you all, especially for those of you that are going into some sort of manufacturing field. You probably want to figure out if you're heating something up, what's the safe temperature to try to work on that sort of that object that you've heated up. And the same thing with cooling it. All right, you want to warm it up, then you would go in the opposite direction of this. So that concludes our first order differential equations. So in the next series of videos, we're going to start looking at second order differential equations, how to solve them, and then two different types of second order differentials.